Hi guys, my name is Ade Ayilawan from Ayilawan Academy, and today I present to you this very interesting mechanics problem called cat and mouse tug of war. The image shows a mouse tugging the tail of a cat around a rough cylinder. The first part of the question asks us, does the minimum force necessary to prevent the rope from sliding depend on the diameter of the cylinder? When we read the meat of the paragraph, it's implied that the force of the mice, italicized F, kind of depends on the diameter of the cylinder, the force from the cat itself, and the coefficient of friction around the cylinder. For this part of the question, we are going to use dimensional analysis, which is a smart name or smart term describing homogeneity of equations. We form an expression relating the force from the mice to the coefficient of friction, the diameter of the cylinder, and the force from the cat, as well as their units. So basically we will be studying their units. The units of force is kilograms per meter per second squared. The unit of the diameter of the cylinder is meters. Coefficient of friction is unitless, so we can already discount that. Now I've made a mistake here. I meant to say that beta, that is the power of the diameter, must equal 0, or else there is no relationship between the right side and the left side. They are not homogeneous. For the left side and the right side of the equation to be homogeneous, the power of the diameter, beta, must be equal to 0. Anything to the power of 0 is 1, so therefore there is no dependency on the diameter of the cylinder. So the force from the mice does not depend on the cylinder. Part B is a bit more involved. To answer this part of the question, I'm going to concentrate on this boxed region and enlarge it so that we can better understand what's going on and describe it. Now, on one end, we have the mice pulling. On the other end, we have the cat pulling, each pulling with their own tensions on the rope around the cylinder, which I'm going to draw in grey. Now the question tells us that the difference between the end of the cat and the end of the mice is pi over 3, as in the angle separating them is pi over 3. And because of the action of the rope against the cylinder being tugged against the cylinder, I have a normal reaction force. So I can draw up or write a differential expression relating the change in tension between both ends to the reaction force, where the reaction force is the result of the difference in tension or the resultant tension at a certain point around the cylinder multiplied by the coefficient of friction. The next few lines are going to be me solving this differential expression using integration to find a solution which will have t equals some function of the angle around the cylinder. So we have our solution for the tension where C, the constant of integration, is something to be found. We can find it using a couple of boundary conditions where at one end of the rope or the cylinder we have what the cats are doing, and at the other end of the cylinder we have what the mice are doing, and all I'm doing is substituting these values of the angle and tension, which is a force, so the force of the cat or the force of the mice, into the expression for tension. What we've done so far is confirm that we have different forces at each end of the rope separated by an angle pi/3. Also, what we've done is we have defined the constant of integration C as italicized F, which happens to be the force from the mice. Here I'm just rewriting our solution, replacing tension with the forces that we were given in the question and putting the constant of integration as F. So I'm reiterating that F represents 10 mice because the question asks us about one mouse. What would one mouse do? So what I'm going to do now is that I'm going to make a second expression which represents one mouse, where the force of the cat stays the same, but the force from one mice, I've called that F dash, and that equates to F, which is the force of the cat, divided by 100, because one mouse is 1/10 of 10 mice, and that would equate to 1/100th of a cat. And here I'm basically implying that there's going to be an angle that we must find, which is θ1. Mu is an unknown, so my next workings will be to eliminate it. So here I'm just going to rewrite our first solution, and I'm just going to replace the pi/3 with θ0, just to make it a bit more cleaner. And I'm going to call that equation 1. What I'm going to do is that I'm going to rearrange it for mu, and then I'm going to substitute mu into our second equation, which is the solution regarding one mice. Now the reason I can do that is because mu does not change. It's still the same coefficient of friction whether 10 mice are pulling it or one mouse is pulling it. And I've written equation 2 like this because we are actively trying to find what the angle needed is for one mice to pull against the tail of the cat to match the force from the cat. So I'm making the angle the subject of the expression. So I've substituted equation 1 into equation 2, and what I'm doing now is that I am cleaning up. So I have the minimum angle needed as a function of some natural logarithms of f and f1. This looks very messy, so what I'm going to do is that I'm going to clean it up using the log base change rule. Now don't be alarmed that I've swapped from natural logarithm to log to the base ff, because the ratio of logs never change. For example, the natural logarithm of 9 divided by the natural logarithm of 8 is equal to log to the base 10 9 divided by log to the base 10 8. So that's how I was able to do that. So I've cleaned it up and I've rewritten my expression as lambda 1 equals lambda 0 log to the base 10 100. I basically just substituted a bunch of values and cleaned up once again. The final solution for the minimum angle needed for one mouse to match the cat is as simple as plugging it into your calculator, and the answer is 2 pi over 3. I hope this video has been very educational. Try it for yourself, and I'll see you in the next video.